We are starting with slide number 33. This is from Chapter 2, Set A of the PowerPoint slides. And we left off, we were talking about solutions, which are homogeneous mixtures. That means that the solute, which is the substance dissolved in the solvent, is dissolved evenly throughout the solvent. The solvent is usually a liquid. Water is typically the solvent. An example of a solution in our body is blood sugar, which is the sugar glucose, is the solute, and the water in blood plasma is the solvent. So water and sugar can be a solution when sugar's dissolved in water, water and salt. Basically, blood plasma has a lot of different electrolytes and ions dissolved in it, particles dissolved in it. True solutions are usually transparent. For example, air is a solution of gases, mostly oxygen and nitrogen. And salt solution, sugar solution, most solutions in the body are solutions of gases, liquids, or solids that are dissolved in water. Now, the way that we express concentration of solution is either a percent. So we would say like a 10% salt solution has 10 parts salt to 90 parts water. Basically, you could do 10 grams of salt, 90 grams of water, and that would be a 10% salt solution. And we also use, in medicine, we use milligrams per deciliter, and that is the units that are used for when we use like a blood glucose test. When we do a blood glucose test, prick someone's finger and test their blood glucose levels, when that meter gives you a number, that number is in milligrams per deciliters. So if it says that your blood sugar is 100, then it's 100 milligrams per deciliter, or 80, And then molarity, which we won't use. I just want to let you know, if you're in chemistry, you will use molarity, but we are not taking chemistry class. So we're mostly going to use concentration or milligrams per deciliter for solutions. And then colloids, also known as emulsions, are just solutions that the particles don't settle out. So the solution is cloudy or milky. So Jello is a colloid, and I know I said blood was, I wasn't thinking. Cytosol, which is the fluid inside of our cells, is a colloid. Our cytosol, which is the fluid in our cytoplasm, that is a colloid, but blood is a suspension. And a suspension is a heterogeneous mixture. So it's not, everything's not mixed evenly throughout the solution. So blood is a suspension. All right, moving on, we are going to talk about the role of electrons in chemical bonding only so that you can understand how chemical bonding works and why it's necessary. But we are not going to go into the same detail you would in chemistry class. So what I really want you to understand is that electrons, however many protons that an atom has, it's got that same number of electrons. And all of those electrons are outside the nucleus. They move very fast, but they do tend to reside in certain energy levels. So, an atom can have up to, and you can think of electron shells as like layers around the nucleus of the atom, kind of like layers of an onion around the nucleus of the atom. So an atom can have up to 7 of those electron shells. And the one on the outside is going to be the electrons that are involved. The outer shell electron or outer energy level electron are the ones involved in chemical reactions. We call them valence electrons. Now, 2 electrons can be in shell 1, but all the rest of the shells, all the way up to 7, will hold larger numbers. And we don't have to learn about that. We don't have to learn how many electrons each shell holds. But what you do have to know is the valence shell electrons, the outermost electron shell, valence shell electrons. That outer energy level can hold up to 8 electrons, unless the outer energy level is the first shell, which can only hold 2. But the valence shell electrons are the electrons in the outermost electron shell or energy level. And the rule that I just said, the octet rule or rule of 8s, is that atoms are more stable. So atoms desire 8 electrons in their valence shell for them to be chemically stable. Except for the smaller atoms like hydrogen and helium, and they are going to be satisfied with 2 electrons in their valence shell because their valence shell is shell 1. But most of our atoms are going to need 8 electrons in their valence shell or outer shell. The noble gases, like helium, already have 8 electrons in their outer shell, so they don't participate in chemical reactions. But most atoms do not have full or complete valence shells. So what they're going to do is they are either going to gain, lose, or share electrons with other atoms in order to achieve 8 valence shell electrons, which will make them chemically stable. So we look at helium. Helium has 2 electrons in its valence shell, and since it only has 1 shell, it's satisfied with 2. So it is stable. It's not going to chemically react with other atoms. It's in the inert gases, which is group 8 on the periodic table. Neon, if you look at its outer shell, has 8 electrons in its second shell or outer energy level. So it's got 8 valence electrons. So neon is also an inert gas, which is stable. Hydrogen only has 1 and needs another 1 in its first shell to be stable. Carbon has 1, 2, 3, 4, so it needs 4 more to be stable. Oxygen needs 2 more. And sodium, really, I know it looks like since its outer shell has 1 that it needs 7, but it would be a whole lot easier if sodium just lost this 1, because its outer energy level would then be the second energy level, which is already filled with 8. So sodium would actually tend to lose 1 electron to be stable. There are 3 major types of chemical bonds which form when atoms gain, lose, and share electrons, and they are ionic, covalent, and hydrogen bonds. We'll start with ionic bonds. Ionic bonds form because atoms lose and gain electrons. They become charged ions, and ions of different charge are attracted to one another, and that attraction produces an ionic bond. So, in an ionic bond, one atom becomes an anion. It takes on a negative charge because it gains 1 or more electrons. So an anion is an ion with a negative charge because it has gained electrons, and it takes on that negative charge because electrons are negatively charged. Another atom in the bond becomes a cation, which is an ion with a positive charge, and it's going to take on a positive charge because it loses 1 or more electrons. If it loses a negative charge, it's going to have an extra proton, one or more protons than it does electrons. So it's going to have an overall positive charge. So again, an anion has a negative charge because it gains electrons. A cation has a positive charge because it loses electrons. So if we go to sodium and chlorine, sodium will be stable if it loses this 1 electron, but it also is going to give sodium a positive charge. And we'll write it this way: sodium ion with a positive charge. Chlorine is going to be stable if it gains an electron. So gaining an electron will give the chloride ion a negative charge. And now you have an opposite charge on each of these ions. The cation is sodium and the anion is chloride. And because they're opposites, they attract. And that is an ionic bond. Now, even though we know sodium chloride is called table salt, there are other salts. There's potassium chloride. There's magnesium bromide. There's calcium phosphate, just a, a salt is an ionic compound. So there are many, many different ones. This is a picture of how ionic compounds the ions in an ionic compound arrange themselves to form a crystal. And then we have covalent bonds, which form when electrons are shared. So if we look here, this is methane gas, and what happens is carbon atoms need 4 more electrons, and each hydrogen atom needs 1 more electron. So if we share valence electrons between all the hydrogen atoms and then the one central carbon atom, that will give carbon now an extra 4, and it will give each of the hydrogens an extra 1. So all of them will be stable by sharing a pair of electrons between them. And that pair of electrons is represented by a single line. So that's called a single covalent bond. Then we have oxygen gas, which forms when 2 oxygen atoms share 2 pairs of electrons, because each oxygen needs 2 more electrons so that it will have 8. So the 2 pairs that are shared here and here are represented by double lines. So this is a double covalent bond. And nitrogen gas is 2 atoms of nitrogen that form 3 bonds, 3 covalent bonds, which is a triple covalent bond that's formed by sharing 3 pairs of electrons, or 6 total electrons, so that nitrogen will have the full 8 electrons in its valence shell. Now, another thing about covalent bonds is that they can be nonpolar. In other words, the atoms in the bond, the atoms that form the bond share the electrons equally. So if it's a nonpolar covalent bond, the electrons are equally shared. Like, for example, carbon dioxide, the electrons that are shared between the oxygen atoms and the central carbon are shared equally. But a polar covalent bond is when those electrons are shared unequally. In other words, one of the atoms has a stronger hold or a stronger pull on the electrons than the other atom does. So if one of the atoms has a greater pull or a greater attraction for those electrons that are being shared, we call it electronegative. So it's going to have a negative charge compared to the other atoms. So it's not got a full negative charge, it's got like a slightly negative charge. So one example of a polar covalent bond is the bonds between oxygen and 2 hydrogen atoms to form water. That makes water a polar covalent molecule. The atom that is electronegative is oxygen, because oxygen it's a larger atom, so it has a greater, stronger pull on the shared electrons. And what that does is it gives the oxygen end, which is the red atom here, a slightly negative charge, and then it gives the 2 hydrogens a slightly positive charge. So that makes the molecule polar. It makes it have a negative end and a positive end, or negative pole and a positive pole. So we say it is polar, okay? And it gives water a lot of properties. So here again is a table that shows you an example of an ionic bond with sodium chloride, a polar covalent bond with water, and nonpolar covalent bond with carbon dioxide. Now, a hydrogen bond is not a bond that forms compounds or molecules. It is actually a weak chemical bond that forms between molecules. So, and there's an animation. This is a good animation to watch. It is slide number 63. Slide number 63, showing you an animation that will teach you about hydrogen bonds. But if you look here at the central water molecule and look at the location and orientation of its oxygen. So the oxygen in that center molecule is slightly negative. It is going to orient itself so that it faces the hydrogen end of the other water molecules that are close by, because the hydrogen ends are slightly positive. and it will cause these water molecules to be slightly attracted to each other. You may have noticed when you spill water that it's going to form droplets or puddles of water. It doesn't spill evenly, and when it rains on your windshield, the raindrops, form droplets and not a even sheet of water across your windshield. That is because the water molecules in those droplets are attracted to one another. It's called cohesion. And they are attracted because of the hydrogen bonding between them. Another thing that hydrogen bonding does is gives water, such as on the surface of a pond, it gives it surface tension. And that allows insects to walk on the surface of the water. Now, our next recording will start with section 2.5 on chemical reactions, and then we'll probably move into slide set B.